Hello, everybody. Welcome to Blackhat 2010. You are in the Milano room, where Aleatory persistent threat is being presented by Nicolas Waisman. He's from Immunity. He's a senior security researcher. Please welcome Nico.
All right, thank you. Can you guys hear me? Yes? Thank you for being here today. As he said, my name is Nicolas Waisman. I'm a senior security researcher at Immunity. I get to manage the Argentinian office of Immunity. So if you find that I have a very weird accent, that means because I usually speak Spanish. But anyways, if you have any question about, because probably I will pronounce some word bad, but you just stop me and let me know. Anyways, before we start, let me tell you what this presentation is not going to be about, so you can leave before we start. We are not going to talk about the Brazilian malware scene. We are not going to talk about the Chinese threat. We are not going to talk about Nigerian scam and stuff like that. In fact, it is my intention that we see the APT from a different perspective, which is what basically I do for a living, which is exploit writing. So my idea will be to start analyzing what companies understand as APT, but from an exploit writing point of view. So before we start, apparently aleatorism is not a very common English word, but it is in Spanish. So the direct translation looks like that. I looked it up in the dictionary, and it was there. So it is a word. But it's a Latin-based word which is based on alia, which it means the roll of dice, which being here in Blackhat makes a double sense, which I didn't prepare. It was just pure luck as this presentation. So when I started with Immunity, like a long time ago, writing exploit, it was all Unix exploit, basically remotes. And then at some point, my boss, Dave, was like, yeah, Unix, not anymore. I have to move to Windows. So we started working on Windows remotes. And then Windows started implementing all the common protections that Linux has, like PAX and GRSEX and stuff like that. And then obviously the war got called because remote exploits were harder. People were investing in improving their servers. So researchers slowly start moving into client side, which are what we are going to talk about today, which are browser bugs. Back in the time, when it started, if you write a browser bug, people will look weird to you, like that is lame, but not anymore apparently. So everyone is moving to browser bugs, and that's what we are doing. And obviously, browser bugs takes a lot of attention for the media, as you can see on the titles there. Why browser bugs? They had some reasons, though. First of all, they're easy to find. Everyone is finding a bug, even through fuzzers. In fact, recently, Aleatory, is that pronounced correctly? He recently released a fuzzer, which still finds bugs on the main browsers. The interesting part about browsers is that the attack surface is huge, because you have from libraries parsing images to two embedded languages such as JavaScript and Visual Basic script. So it's big, the amount of things you can attack. At the same time, it's easy to exploit because you have a whole interpreted language that you can manage to do stuff in order to exploit it reliably. And then they are widespread. Everyone uses a browser. And obviously, it's a client side, and the client side is an open world to a network. So from that point on, you can get to the real thing. So that's why researchers and malware and bad guys are doing a lot of browsers. In any case, the big word is advanced persistent threat. That was a word invented, I think, by a company called Mandiant or something like that. I think they do government contracts. Basically, there was some kind of hypothetical attack against Google. It was called Operation Aurora. And then someone thought that it was a cool name to call it Advanced Persistent Thread, which the bug itself was basically a client-side bug, and someone just owned machines. In our case, we're going to analyze a different bug, but it's pretty much the same as Aurora. The only thing is that it's newer, so I thought that if we're going to analyze a bug, let's make one which is newer than the Aurora bug. So let's talk about a little bit about what we are starting from the exploiting standing point of what advanced persistent thread means. In the case of advanced, we divide it in three different terms. For instance, the first one is stealthiness. Stealthiness has three steps, obviously, as every penetration test. The first part is obviously the one that's related with fingerprinting whatever you are trying to exploit, and that needs some stealthiness. You cannot make much traffic on the network, or else you get caught. The second part is obviously related with the exploitation part, which you need some kind of encoding not to get caught by antivirus, IDS, etc., etc. And finally, it's obviously the post-exploitation phase, where you don't have to be caught by whatever host intrusion detection system your attacker had, or an antivirus. Now, about reliability, that was a difficult word to divide, because robustness and reliability are pretty much similar in a way, but we try to understand it differently. With reliability, we mean the part where the actual exploit primitive works. So that means, like, if you're exploiting a Stack Overflows, the reliability part will be the part that you do the whatever mem copy, string copy, etc., and you get EIP. Only that specific part. That's why we, it's a definition, and that's the one we use. In the case of robustness, we think as an exploit being robust as the reliability in general, and that means the fingerprinting part, because nowadays every exploit needs a way to identify exactly which is exploiting. The part where you do a lot of QA in order to make it as universal as possible. And the part where it works. The shellcode has to try to identify all the potential errors that you can have on the different targets that you can potentially have, or network fluorescence, etc. And your shellcode has to handle all of that. And so that is all part of the robustness of an exploit. And then the other part is the persistent thread part, which in a way we cannot separate those words, because persistent thread indeed is a tautology. Because in our perspective, especially if we are talking about client-side exploit, you cannot say that a thread is not persistent. I mean, obviously, there are worms that get into networks and do stuff, but they're not a real threat. A real threat is the guy that gets into your network and starts sniffing your network, start doing man in the middle, start exploiting your VM set from their client side, etc., etc. So a real threat will be the threat that is persistent, and that's why those words cannot be separated from each other. So one of the things that I always thought about each time I see one of those bug get releases, like the Aurora bug or the ear-pierce bug, which is the one that we're going to talk about later, is that how those things get caught in the wild, though. Is there a guy like looking at that Wireshark like full day or what? And I came up with like 3 different options. 2 of them I crossed it down later. It's obviously IDSS doesn't do anything against ODAs. They are parsers. So basically, you're putting a parser inside a parser in order to protect your network. And those parsers just look for signatures or protocol anomalies, which is not usually the case of a bug. And you can have like IDS ODA protection, which in a way works like a mafia, because like I find my own ODAs and I will protect you against my own guys. So that's basically how ODA protection works. And then you have honeypots, which, as far as I know, never found anything. I don't know if anyone knows of a bug that was found for a honeypot, but I don't recall anyone. So we get to the last point, which is basically what we are here for, which is unreliable exploit. Unreliable exploit are pretty much the only reason why ODEs get caught in the wild. And that's why we're going to talk about today, basically how a lot of the bugs which were found on the wild were basically found because they were bad written, especially related with client side. So let's talk a little bit more about bugs. Since obviously the advance of software, a lot of people getting conscious about bugs, about vulnerable API functions and stuff like that. The common memory interruption bug is pretty much dead. Obviously, you can still find it, but most of the bugs these days are related with things a little bit more complex. And that is the case of use after free, which is basically what we're going to talk about today. Use after free bugs are the new memory corruption in a way. Almost all the last client-side exploits were use after free, at least the important ones, obviously. And basically, the definition of a use after free is really, really simple. So basically, a use after free is memory that is used after it was previously deallocated. So to make it even easier, I put a timeline, and you have two moments. You have the first moment where objects get free. I mean, I'm looking like a 2-year-old teacher, but at some point, I bet it's going to make sense, because I will explain why I'm explaining this way. So we have a timeline. We have the first moment, which is an object gets free. Then we have a second moment, which means the object gets used. So something in the middle happens, and the object gets replaced for something else, and then it gets exploited. That's how usually use after free works. If we can go back in history, I think that in a way, a double free bug, which was common some time ago, is in a way a use after free. Some memory gets free, and then gets double free at some point. So in a way, it's similar in the concept of a use after free. So finding a use after free, I mean, you can still find it by fuzzing, which is good. Finding it by auditing, it's not that hard, but obviously it's going to get harder and harder each day. This is three of the common techniques. There's a really nice paper written by Mark Doe, Ryan Smith, and I don't know the other guy's first name, Dewey something. What's his name? David Dewey. Sorry, David, if you're here. Basically, the first method is the most common one, which is basically a method or a property is retaining an object, and it forgets to increment a counter. All the objects has a counter. A counter helps you to keep a track of where an object has been used. So basically, each time you want to use an object or save it somewhere, you have to increment the reference. So you can say that I'm using that object for this time, and when I stop using that object, I basically decrement that counter. Very simple. So basically, the most common bug is a method or a property actually storing the objects without incrementing the counter, and so at some point that counter gets free because nobody told you that you were using it, and then my property still has a reference to that thing, but it was free, so I use it. Then I got execution, obviously with a little more work. Then you have shell copies, which is in a way pretty similar, and it was the Aurora bug, which basically you are just directly